we have been working out problems related to the first law of thermodynamics applied to control mass systems, and we will continue with the problem solving exercise. Let us look into the problem 3.6. A computer in a closed room of volume 150 meter cube dissipates energy at the rate of 10 kilowatt. The air in the room was at 300 Kelvin 100 kilopascal when the air conditioner suddenly stops. What is the temperature after 15 minutes? So, this is a typical situation when the computer is in a AC room and suddenly the AC stops working. So, the room will start getting heated because of heat dissipation from the computer. So, after 15 minutes what will be the temperature? So, here the control volume, so you can make a schematic. So, you have a computer like this, your control mass system is this region. So, the region minus the computer. So, room minus computer is the system. So, here is the computer, room minus computer is the system. So, let us apply the first law of thermodynamics for this system. So, what is given? V room T1 is 300 Kelvin and pressure is 100 kilopascal. It shows that it is reasonably low pressure. So, air can be treated as an ideal gas without much of a problem. So, Q12, the first law if you apply, so here there is no work done and this Q12 is the heat dissipation rate of the computer times the time. So, heat dissipation rate of the computer is given as 10 kilowatt and the time is 15 into 60 second. So, U2 minus U1, if we treat air as a calorically perfect gas, then this is mCV into T2 minus T1. So, what is mass? The volume of the room is given and what is P1? P1 is 100 kilopascal, R of air is 0.287 kilojoule per kg Kelvin and T1 is 300 Kelvin. So, from here you will get what is M. So, that M if you substitute here, Cv of air you can calculate by noting Cp minus Cv equal to R and gamma equal to Cp by Cv, which is roughly 1.4 for air. So, from that you can calculate Cv and T1 is 300 Kelvin. So, from here you can calculate what is T2, this is 372 Kelvin. So, you can see that in a room where computer is working, if the AC stops, how quickly the room can get heated. We will work out another problem. The next problem, a piston cylinder contains 2 kg of air at 27 degree centigrade 200 kilopascal as shown in the figure. The piston is loaded with a linear spring, mass and atmosphere. Stops are mounted so that V stop is equal to 3 meter cube, at which point 600 kPa is required to balance the piston forces. The air is now heated to 1500 Kelvin. Find the final pressure, volume and work done and heat transfer and work done on the spring. Okay. So, let us draw the schematic. So, our system is this air, M is 2 kg, state 1, T1 is 27 degree centigrade, P1 is 200 kilopascal. So, you can find out what is the volume at state 1, P1 V1 is equal to M R air into T1. This is 27 plus 273.15. This has to be in Kelvin. So, you will get what is V1. So, completely specify state 1. Another hypothetical state is given that at V stop, that is 3 meter cube, 600 kilopascal is required to balance the piston forces. So, two hypothetical dash, this is as we have seen earlier that such hypothetical states are given to construct the PV diagram, the locus of pressure versus volume data. So, you have V2 prime So, let us draw the PV diagram. So, you start with state point 1, you end with state point 2, but the locus of the PV state points between 1 and 2 is guided by this linear spring, and the state point 2 prime is located on this. The actual state point 2 is somewhere in between these two. So, in between means it could be on the other side or this side, that we do not know, but it is, we know that it is located on the straight line 1 to 2 prime. So, from the equation of the straight line we know So, let us see what is known here. P2 is not known, at state 2 only temperature is known, which is 1500 Kelvin. P1 is known, P2 prime is known and P1 is known, V1 is known, V2 prime is known. So, you can write here P2 as a function of V2, but you do not know separately P2 as a function of P2 or V2. So, this is equation number 1, but you have another equation connecting P2 and V2. What is that? You have P2 V2 is equal to MR T2. This T2 is this 1500 Kelvin. So, you have P2 V2, you know this is 2. So, you solve 1 and 2 simultaneously. There are 2 equations and 2 unknowns which are P2 and V2. So, you solve these simultaneously. So, you will get what is P2 and what is V2. So, once you get P2 and V2, you can identify state point 2. So, what is your work done? This is 367.3 kilojoule. Heat transfer, now here is an important point. The point is that air is an ideal gas, I mean air can be approximated as an ideal gas under these conditions. So, you can write du is equal to Cv0 dt. So, u2 minus u1 is integral of Cv0 dt, and this Cv0 is a function of T. It cannot be taken as a constant for this problem, for the reason why it cannot be taken as a constant for this problem, because think of the temperature range. T1 is 27 degree centigrade, that is 300, around 300 Kelvin, and T2 is 1500 Kelvin. So, you can see this is 1500 Kelvin. So, from 300 to 1500 Kelvin, this wide range of temperature is such that you cannot assume this Cv to be a constant. So, Cv as a function of temperature has to be known, and once this is integrated between states 1 and 2, U2 minus U1 can be obtained. For saving this labor, these numerical integration values are tabulated in the form of a table called as air property table in any thermodynamic data book. So, you will see it in the appendix of any thermodynamics book that you are referring to. So, once you do that, once you refer to the air table, you can calculate this U2 minus U1. So, the key to getting the correct answer is, do not assume Cv as constant here, but look into the air table to calculate U2 minus U1. So, once you do that, the net heat transfer is okay. So, we will work out perhaps one more problem before we call it a day for this particular lecture. Let me erase the board first before we look into the problem. So, the problem is problem 3.8. So, here you have a 10 meter high cylinder with a cross sectional area of 0.1 meter square. It has a massless piston at the bottom with water at 20 degree centigrade on the top. Air at 300 Kelvin with a volume of 0.3 meter cube under the piston is heated, so that the piston moves up, spilling the water out over the side. Find the total heat transfer as all the water has been pushed out. Okay. So, let us draw a schematic of the problem. So, this h is a variable h. As the water is spilling, this height is decreasing. The gravity is in this direction. So, the height of the cylinder, let us call it capital H, out of which we neglect the small thing, because capital H is 10 meter. So, 10 meter out, from 10 meter this will be maybe at the most few centimeters, that can be neglected. area of cross section is 0.1 meter square. This water is there at 20 degrees centigrade. Now you tell me what will be the control mass system for this problem? Air, water, air plus water, what? See, water cannot be a control mass system here because water is continuously spilling. So, because water is spilling, the mass of water is not remaining the same here, but air is trapped under the piston. So, although the piston is moving, the air is remaining same in mass and identity. So, this is the system. Okay. So, for this system we have T1 as 300 Kelvin and V1 as 0.3 meter cube. What is P1? Atmospheric pressure plus pressure due to the water column. So, H1 rho water G. Rho is 1 by specific volume. So, how do you estimate the specific volume? This is approximately Vf at 20 degrees centigrade. Okay. So, now what is this H1? So, you have 10 meter high cylinder minus the height of the air. So, air has a volume of 0.3 meter cube and it has a cross sectional area of, the cylinder has a cross sectional area of 0.1 meter square. So, height of this one is 0.3 by 0.3 by 0.1. So, H1 is 10 meter minus that. Okay. So, if you calculate, put all these data, you will get P1 as 169.84 kilopascal. What is P2? When state 2 is when all the water is spilled. So, P2 is nothing but P atmosphere, which is given for this problem as 101.325 kilopascal. What is V2? V2 is now this entire volume is air, all water has gone. So, it is H into A. So, this is 10 meter into 0.1 meter square. So, that is 1 meter cube. So, if you draw a PV diagram for this process, this is state 1 and the final state, more volume, less pressure. What will be the locus of this? The locus will be a straight line. Why straight line? There is no linear spring. So, why straight line? Because the pressure varies linearly with height. So, the displacement volume V is nothing but this height into the cross sectional area. Cross sectional area remaining fixed, the pressure is linearly related to the volume. So, this is the PV diagram, one of the most important parts of this problem. So, work done. So, that is not a part of the problem. Part of the problem is what is the heat transfer. So, if you apply the first law, in this case you can approximate, the temperature range is not supposed to be that high. So, you can approximate this as possibly Cv0 into T2 minus T1, but that you can check only after you obtain T1 and see whether this range is very large or not. So, how do you obtain T1? You know P1 V1 by T1, sorry, how do you obtain T2? You know P1 V1 by T1 is equal to P2 V2 by T2. So, P1 V1 T1 everything is given, P2 and V2 are known. So, from here you will get what is T2. So, if you substitute all these values, you will get what is the total heat transfer. So, this is equal to 220.7 kilojoule. Okay. So, to sum it up, we have worked out various problems related to the first law of thermodynamics, and in these problems we have mainly focused on control mass system. The issue is that instead of a control mass system, if we deal with control volume, what will be the change in the mathematical paradigm of expressing the first law? We will take up that in one of our next lectures. Thank you.